So equilibrium constants do depend on temperature, because temperature affects, well, it affects several things. So you'll often see that the temperature is specified, but it does not come into the calculation. So if it says this is this at 25 degrees Celsius, that doesn't mean you need to use that number in a calculation. They're just saying it's true at this temperature. Concentrations, when we're calculating these constants, are always in moles per liter, but we drop the units. Okay, so you've been wanting to drop units for 3.5 weeks, right? Now you get to drop units. I'm telling you to drop the units. We just understand that the units are moles per liter. The units on the equilibrium constant would be different because of the different, how many squared and how many cubed, and it would just be ugly. Yeah, so for when we're doing equilibrium constants, we understand that if we have a concentration, it has to be in moles per liter, but we're not going to write the units when we calculate KEQ. And KEQ is going to end up with no units. Could you guys get those doors, please? People are loud. So the equilibrium constant is a constant. That means it doesn't change. So at a given temperature, the equilibrium constant is always the same. The concentrations will probably change, but their relationship as described by the equilibrium constant doesn't change. So let's look at this reaction. We've seen this one before. H2 plus I2 gives us 2HI. Suppose a mixture of H2 and I2 is allowed to come to equilibrium at 445 degrees Celsius. The measured equilibrium concentrations are, so the concentration of hydrogen is 0.11 moles per liter, iodine is 0.11 moles per liter, and HI is 0.78 moles per liter. What is the value of the equilibrium constant? This temperature is just identifying the temperature that it's happening at. We don't have to use that. It's just there. To calculate the equilibrium constant, we first have to write the expression for it. So KEQ, it's the products. So here this is HI. That's a gas, so we're going to include it. And that would be squared. Divided by the hydrogen concentration. Exponent is 1 because the coefficient's 1. And the iodine concentration, again with an exponent of 1. After you do that, then you take the numbers that are given and you plug them in. So the hydrogen ion concentration is 0.11 moles per liter. So that's down here, 0.11. Just drop the units. I2 is 0.11, so that goes over here where I2 is. And then HI is 0.78, so that goes up here. But the hydrogen iodide concentration is squared, and so this is squared. And now you need to make sure that you can communicate with your calculator. So I'm going to do 0.78 and press the x squared button. And then I'm going to divide by 0.11 and divide by 0.11. And I'm going to come up with 50.28. And we're going to go ahead and follow the rules of sig figs here. So we should have two significant figures. So 50 with a decimal point, or 5.0 times 10 to the 1. No units on the constant. Any questions? Be careful when you're dividing by two numbers that are multiplied. If you want to multiply those, you got to put parentheses around them. So this is, I think, a useful table from your textbook that when I made these slides was not available from the publisher, and so I had to take a picture of the book and stick it in my PowerPoint slides. This is just illustrating how, for this given reaction, where we found at the conditions we were given right here, that the equilibrium constant was 50. So that might happen if you started with half a mole of each of these and none of that. If you started with no reactants and half a mole of product, the equilibrium concentrations would come out to this, and they're still going to equal 50. If you started with an equal amount of all three, the reaction would occur until those concentrations give us the same equilibrium constant. So it doesn't matter what you started with, the reaction will proceed in the forward and or reverse direction until the equilibrium constant is achieved. Any questions? Let's do another one. So here we've got this reaction. CO plus 2H2 gives us CH3OH. So a mixture is allowed to come to equilibrium at 225 degrees Celsius. Do we need that number? No, just information, just extra stuff. The measured equilibrium concentrations are given right here. What's the value of the equilibrium constant at this temperature? See, the equilibrium constant might be different at a different temperature. That's why it's specified. But we're not going to worry about it. We're just going to say, oh, well, they just threw that in there. It's fine. So we have to write the equilibrium constant expression for the chemical reaction. Look through at the state symbols. If there's any that are liquid or solid, just mentally or actually cross them off. Here they're all gases. So products, product concentration, this has no coefficient, so I don't have to put an exponent. And then divided by the reactant coefficient, reactant concentrations, CO is 1, and H2 has a coefficient of 2, so I have to square that. Products divided by reactants, the coefficient becomes the exponent. I'm given the concentrations, I just need to plug them in. So the concentration of the methanol is 0.151. The concentration of the carbon monoxide is 0.489. And the hydrogen is 0.146. And that one is squared. So on my calculator, I'm going to do 0.151 divided by 0.489 divided by 0.146 squared equals. I'm getting 14.486. I look at my concentrations, they all have 3 sig figs, so I could express this as 14.5 is the equilibrium constant at this temperature. Any questions? So the point of this is not to just calculate equilibrium constants for the fun of it. We use equilibrium constants to predict the reaction, the concentrations of the reactants and products at equilibrium. So we start with this much this and this much that, and we put them all together, and we want to know, well, what's the concentration of this going to be? That's what it's useful for. So if we are given the equilibrium constant and all but one of the concentrations, we can find that concentration. So we need to write the equilibrium constant expression. That comes from the chemical equation. So KEQ. divided by reactants This one has a coefficient of 2, the reactant, so I have to square that. They're asking me to find the concentration of CO2. So CO2 is one of these. I've got CF4, I've got COF2, I've got KEQ. I just need to rearrange this equation. So I'm going to end up with CO2 is equal to KEQ times COF2 squared divided by CF4. If you have trouble rearranging those, please come talk to me. So now I'm just going to plug the things in. 2.00 for the equilibrium constant. COF2 is 0.255, and that's squared, divided by the CF4 concentration, 0.118. So 2 times 0.255 squared divided by 0.118 equals so the CO2 concentration equals, everything has 3 sig figs, so I'm going to write this with 3, 1.10, and then we bring the unit back, capital M. Yeah?
Would it be wrong if you put the 2 first and then filled it in and then solved it up? Or did you have to do that?
Would it be wrong if you stuck 2 in for KEQ and then rearranged it? No, it wouldn't be wrong. I think in general it's preferable to rearrange an equation before you put numbers in, but I'm not going to say you can't do that. You certainly can. I just see people do some funny things sometimes. Of course, I see people do funny things no matter what I tell them to do because people are funny. That's what makes you guys interesting. Any other questions? So we just suspend units for these calculations. These all are in moles per liter, except for KEQ doesn't have any units. And when we calculate a concentration, we just slap a capital M on it. It doesn't come from anywhere. Let's do another one here. Diatomic iodine decomposes at high temperature to form iodine atoms according to this reaction. Here we're given the equilibrium constant. So this equilibrium constant, 0.011, what does that tell us about which there's probably more of? Are there more products or more reactants? There's more reactants. So a small KEQ means that the reaction does not go forward very much. A large KEQ tells us it goes forward a lot. This one's small. Not horribly small, but it's definitely less than 1. So to do this, we need the equilibrium constant expression. So it's going to be the product, which is just iodine atoms squared, divided by the reactant concentration. So we're given that the concentration of I2 is 0.1. They're asking us what's the concentration of I. So here we're solving for I. So if you can think of this as cross-multiplying or multiplying both sides by I2, I'm going to end up with I squared being equal to the equilibrium constant times the concentration of I2. Here I have what I want, but it's squared. How do I undo a square? Square root. Square and square root are the opposite functions of each other. So what I'm going to do is I'm going to take the square root of both sides. The square root of something squared is just the something. So now I've got the iodine atom concentration is equal to the square root of the equilibrium constant times the iodine molecule concentration. So KEQ 0.011, and the iodine concentration is 0.10, and I've got the square root of all of that. So 0.0, well actually on my calculator I'm going to do the square root button first. 0.011 times 0.1 and press equals. And this tells me 0.033. 2 sig figs. And I slap the unit on there, molar. So which is there more of? The reactant at 0.1 molar or the product at 0.03? There's more of the reactant at equilibrium. This relatively small equilibrium constant tells me there's going to be more reactant than product. Any questions?